October is our first lesson of the new semester, and I just want to give a shout out to my amazing fourth hour who really brought it this week, and so I'm so proud of you guys. And so what we're going to do so that we don't get too far behind, we'll do this lesson over the weekend, try to jump into that homework, and Monday we'll address any questions that you have. So in our warm-up, I am sure you recognize this famous person right here, and we may have talked about that there's certain things that we identify with Elvis Presley as style music, his clothing, the sideburns. So an identity is something that we associate. So for this super, you might associate with me or the children, but we're going to be talking about trig identities. So one important relationship that we learned back in the day with geometry that we associate with right triangles is a squared plus b squared is equal to c squared. So that is an important relationship that we identify with right triangles. Another thing that is important to for this lesson is important to know is just what is the even function. So I'm going to put that right here, that f of x is equal to the function when you put in the opposite value. So for instance, x squared, if you put it in 2, you put in a negative 2, you get the same output. And that's true for any input in its opposite. For an odd, you put a value into a odd function, you will get the opposite output when you put in the opposite input. This is kind of like the notation, function notation for even and for odd. So I've drawn the cosine function. What we want to do here is identify which trig functions are the 6 trig functions, which ones are even. So if we look at cosine, which is right here, this graph, we can see that cosine is reflective over the y-axis. So that means that this property would be true. If I put in pi over 2, I put in the opposite negative pi over 2, the cosine ratio would be the same. So cosine is an even function. And because secant is the reciprocal, I'm just going to draw in the reciprocal. And we would have those vertical asymptotes going through there. That it would be an even function as well. So the two even functions are cosine and its reciprocal is the secant.
So when it comes to an odd function, which what we have right here, all of our other trig functions are symmetric to the origin, which is what's true when you put in an input and you put in its opposite, you'll get the opposite y value. So for sine, secant, tangent, cotangent, look at those graphs, what we learned in chapter 4, all of those are considered odd functions. So 2 are even and the other 4 are odd. Alright, so what you need to know is identities are going to be a really big deal in chapter 5, and there's a ton of them. So what you need to know is that these are really powerful in college level mathematics, in engineering, physics, and what they do is they allow us to manipulate trig equations and expressions that involve sine, cosine, secant, cosecant, etc. Alright, so we're going to be learning a lot of identities and we're going to be learning a lot more in future lessons. So what is it? It's a statement of equality between two expressions that's true for all the variables for which they're defined. So we're going to be giving you an example of that. Okay, so that set of values where two things are equal is called the domain of validity. Okay, so let me give you an example of something algebraic. So here's a rational expression, that we've probably seen in semester 1, and I think we would all agree that the left and the right are equal. They have an equivalence to them. But is it true for all values for x? And the answer would be yeah. Let me spell that correctly. That would be true for all x where x is not equal to -3. So with our first expression, it's undefined there. But for 4, 10, 12, -2, these two expressions would be equal. So this is an example of an algebraic identity. Now our chapter isn't going to focus on algebraic identities, it will focus on trig identities. So a couple that you probably know, we just didn't call them an identity, would be tangent of theta. That is equal to sine of theta over cosine of theta. I call this the Tractor Supply Company. This would be true as long as cosine of theta does not equal 0. So that would be the domain of the validity for this relationship. We're going to be talking about a lot more. But this is an important ratio to know for the tangent function. So we know that the reciprocal of 2 is 1/2, and that's easier to see if we put that as 2 over 1. So these are identities that we already know. Our first one, sine of x is equal to 1 over cosecant. And we would all agree that cosecant is equal to 1 over sine of x. So these are reciprocals. And again, this is true for all x inputs as long as cosecant of x isn't equal to 0 and as long as sine of x isn't equal to 0. Now, this didn't record the way I wanted it to, so I'm going to write down the other identities and make sure that you know these. And if you have any questions, let me know. So here's all our official identities that we should know. Cosine is 1 over secant, secant is 1 over cosine, tangent is 1 over cotangent, cotangent is 1 over tangent. So these are all reciprocal identities. And then we have quotient identities. A quotient is a ratio. So tangent is a ratio of sine over cosine, and cotangent is a quotient of cosine of x over sine of x. Again, true for all x values. For this one, as long as cosine of x doesn't equal 0, and for this one it's true as long as sine of x doesn't equal to 0. So we have 6 up here and 2 down here that are not new identities, but they're identities that we're going to be using in Chapter 5. So make sure that you know them. Okay, so now for some new identities. And we're going to have 3 Pythagorean identities that I'd like to show you. So we're going to go back to a concept that we learned in Chapter 4. We're going to have the unit circle with the radius of 1. I've drawn in the blue triangle, and the adjacent side we call x, the vertical side we call y. So that's going to give me a coordinate to a point on the circle, xy. So what we know from our trig is that x is equal to cosine of theta. So there's theta right there. And y is equal to sine of theta. And so that's what we use to get coordinates on the unit circle. So because our shape is a right triangle, we know that x squared plus y squared has to equal 1 squared. And this just comes from the Pythagorean theorem. So what we're going to do is we're going to just simply use this relationship for solving for the adjacent and the opposite sides. So we can do a substitution and we get cosine squared of theta plus sine squared theta is equal to 1. That was very simple by just knowing this relationship. So this is our first Pythagorean identity. Where did it come from? The Pythagorean theorem. How? using the relationship between the adjacent side and the opposite side. So this is a very, very important identity that you want to know. Now there's two other versions that are going to look different, and they're really not hard to get. So because this is an equation right here, we know that with equations you can add to each side, subtract from each side, multiply each side, divide each side. As long as you're doing the same thing to the left and the right, we're going to maintain this equality between the left and the right. So what mathematicians did is they said, hey, let's manipulate this identity, cosine squared of theta plus sine squared of theta is equal to 1. So what they did is they said, well, what would it look like if I decided to divide each side by cosine squared theta? So I'm going to do that on each side. And the reason we're going to do that is because I can get different trig functions by doing that. So what I'm going to do is break this up then. So I would get cosine squared theta over cosine squared theta plus sine squared theta over cosine squared theta is equal to 1 over cosine squared theta. So where did that come from? By just dividing each side by cosine squared of theta. Why did we do that? Because we had a cosine squared of theta right there. So obviously this first ratio is going to give us a 1, and this is going to give us sine of theta over cosine of theta squared. So that's a property that we're using, and this would be 1 over cosine of theta squared. So we know that sine over cosine from our quotient identities is of course tangent, so this is 1 plus tangent of theta squared. So I can write the two outside parentheses, but what we tend to do in higher level math is just put that 2 right there. So that means tangent of theta times tangent of theta. And then I'm going to put an equal sign, and 1 over cosine is secant, and that's being squared. So I'm just going to put the 2 right there. So this right here is a variation of our original that came right up there. So there's number 2. So whenever you see an equation or expression that has a lot of things that are being squared, that's usually a sign that you're going to want to use the Pythagorean identity. But we do have one more to show you. So what I did is I wrote the Pythagorean identity, the original, right here. So we're going to do the same thing. We're going to divide each side. This time we're going to divide by sine squared of theta. So do that to each side. And I'm going to get cosine squared of theta over sine squared of theta plus a 1, because sine squared of theta divided by sine squared of theta is 1. Then over here I'm going to get 1 over sine squared theta. So not really a huge step from what we did to get the second identity. We know that cosine over sine is cotangent. So this is going to give us cotangent squared theta. There's a plus 1. And we know from our reciprocal identities that 1 over sine is going to give us cosecant. So this would be cosecant squared theta. So there you go, folks. There is a third identity. Where did these 2 on the bottom come from? By just manipulating the original. So I'm going to just write that. I'm going to highlight it. So here we go. It's this one right there. That's our original right there. So 3 identities. Practice them, but my advice is to just know this one right here really, really, really well. And it's just a matter of dividing each side by either the first term or the second term. And then I'll get this and this identity. Those are called Pythagorean identities. All of them have a 1 in it. All of them have a trig function that's being squared. And we're going to be using those later on in our lesson. So this is what I'd like you to do. is I'd like you to stop the video and I'd like you to try these two examples, okay? Now I'm going to go through them in a minute, but just see if there's a way of using reciprocal or quotient identities to solve for what they're asking you to find. So here we want to know what secant of theta is, and here we'd like to know what sine of x is. We will be using those Pythagorean identities, just not right now. Alright, let's see how you did. So the reciprocal identity, secant of theta is equal to 1 over cosine of theta. So if I know that cosine of theta is 3 over 4, then secant of theta would have to be the reciprocal, which would be 4/3. Tangent, we know, is the ratio of sine over cosine. So if I'm given secant of x is equal to 5/4, I know what cosine of x is. So tangent of x is sine over cosine. This is one way to do it. Maybe you did it different. And they give us a tangent ratio, which is 3/4. And I want to know what sine of x is. So I'm going to divide that by the cosine ratio, which is 4/5. So this is really a equation just with the sine of x in it. So what I'll do is I'll multiply this side by 4/5, and I'll multiply this side by 4/5. And doing a little bit of easy math here, I get 3/5. So sine of x is equal to 3/5. Hope you got that. Let me know on Monday if you have any questions. In example 2, we're in familiar territory of the 4 quadrants, and they're giving me clues. So one of the clues is that cosine of theta is less than 0, which means that it's negative. So I know that when I'm dealing with triangles and ratios, I can't be in quadrant 1, and I can't be in quadrant 4. So that leaves the two ratios, or let me step back, the quadrant 2 and quadrant 3. Now what I notice right here is that cotangent of theta is equal to 2. So what's important to know there is just what quadrant can I be in? Could it be 2? Could it be 3? Well, based on cotangent being positive, I know that I can't be in quadrant 2. So that leaves one and only one quadrant that I'm going to analyze and find these two ratios right there. So there's my right triangle drawn in there, and I'm going to use this clue right here that cotangent is equal to, cotangent of theta is equal to 2. So that would be the same thing as saying that tangent of theta is equal to 1/2 because they are reciprocals. So I'm going to use that because I like tangent. Opposite over adjacent would give me those values, would give me a ratio of 2 for cotangent and 1/2 for tangent. So what I'm going to do is I'd like to know what the hypotenuse is because that's important for figuring out sine of theta and cosine of theta. So again, we'll go to that Pythagorean theorem. 1 squared plus 2 squared is equal to r squared, with r being the radius of the unit circle. And I'm going to get 5 is equal to r squared. So I'll root each side, and I get r is equal to the square root of 5. So I'm going to put that in right there, square root of 5. So now that I have all three sides, it is a total snap to get our sine ratio, cosine ratio, any ratio that they want to know. So we'll do those right over here. So from that angle, sine is opposite over hypotenuse, so it's going to give me 1 over root 5. And just a very important thing, whenever you do a trig ratio, you always want to ask yourself, can it be a positive ratio or is it a negative ratio? So because I'm in quadrant 3 and the opposite is going down, that means that that's going to have a negative ratio. So rationalize the denominator. I'm going to get negative root 5 over 5. That would be my sine ratio. So now we're going to do the cosine ratio, and same thing. So cosine, I'm going to be comparing the adjacent to the hypotenuse, and again, in quadrant 3, that's a negative ratio once again. So the adjacent is 2, and over the hypotenuse, which is root 5. So rationalizing the denominator, I'm going to get negative 2 root 5 over 5. And there's my cosine ratio. Now, we have many cofunction identities, and we're going to kind of lead into this. So don't forget, we're just going to skip example 3, not a big deal. I want to focus on these cofunction identities. So what I've done is I've drawn a 30-degree reference angle, and we know that across in the unit circle, across from the 30 is a half, across from the 90 is a 1, and the other side would be a root 3 over 2. So we saw that in geometry, algebra 2, pre-calc, we know those well. So if we have a 30-degree angle for one of the other two non-right angles, it's pretty easy to get what this angle would be, and that would be 60 degrees. And there's a relationship between these two, and if we have 90 degrees right there in the corner, there is only 90 degrees that's left for the other two. So if I've got a 30 for the reference angle, the other one's got to be a 60. So this is the deal with cofunction identities. It's very simple. So we're going to do a trig ratio, and we're going to do sine of theta at 30 degrees, and we're going to compare the opposite to the hypotenuse, which will give us a half. Okay? So this is the idea with a cofunction identity. So we can do this with any trig function that we want. So if we do it with tangent of 30, I'm going to compare from the 30 the opposite over the adjacent. So that ratio of 1/2 divided by root 3 over 2 is going to give me 1 over root 3. And that's going to give us root 3 over 3. So using the 60-degree angle, is there a trig function that I can use to get the exact same ratio? Well, it wouldn't be tangent, it wouldn't be sine, it wouldn't be cosine, it would actually be cotangent of 60. So with cotangent, I'm going to compare the adjacent, which is right here, to the opposite, which is right there, and I'm going to get that exact same ratio that I did before. So what do we know? That tangent and cotangent are cofunction identities. For any angle on a triangle, if I use one angle in the right triangle and I use the other angle, I would just use the cofunction of that original. So let's do one more. We did sine and cosine, tangent and cotangent. What if we did, what about secant? Secant of 30. So I know that secant is related to cosine. Cosine is the adjacent over the hypotenuse. So that would be root 3 over 2. So this is just going to be the reciprocal of root 3 over 2, which would give me 2 over root 3, which rationalizing gives me 2 root 3 over 3. So from our right triangle with the 30-degree reference angle, secant of 30 is 2 root 3 over 3. Well, what if we use the other angle, the 60-degree? And I wonder what trig function I can use off that 60-degree angle so that I would be comparing two sides and getting 2 over root 3, which is 2 root 3 over 3. And that ends up being cosecant of the 60-degree. So that's going to be a cofunction of the secant function. So sine, cosine are cofunctions. tangent, cotangent are cofunctions. Secant and cosecant are cofunctions. So this is where we're going to pull it all together. If I have an angle and I don't know what it is, what can I do mathematically to get this angle right here? So what we know about that angle up at the top is I know that theta plus that angle that I don't know has to equal 90 degrees. Now, what we learned in our Unit 4 is that 90 degrees is pi over 2. So if I want an expression for that top angle that I don't know, I can simply subtract theta from each side, and that unknown would be pi over 2 minus theta. So that's what we're going to call this angle right there. Pi over 2 minus theta. So this is just using the angle sum theorem. I know that I've got 90 degrees in that corner, which means these two right here have to add up to 90, and this is a relationship. So all we're going to do is use this concept with all of these cofunctions right here for any right triangle. So maybe I have a 30-degree angle, maybe I have a 20-degree angle, maybe I have a 10-degree angle, but the cofunction identities come from this concept that the complement of each one of those angles, there's another trig ratio that will give me the exact same ratio. So here we go. If I do the sine ratio of theta, which is right there, I know that that's going to be the exact same ratio of cosine of that top angle, which is going to be pi over 2 minus theta. If I do the tangent of that bottom left angle that I'm calling theta, that will be the exact same ratio as cotangent of the other angle, which is pi over 2 minus theta. And then secant of theta is going to equal its cofunction, which is cosecant of pi over 2 minus theta. And it works the other way as well. So I'll give you the other three. So here's the other three trig ratios. So if I do cosine of that bottom left angle, that's going to equal sine of pi over 2 minus theta. Cotangent, its cofunction is tangent, and I would use the top angle, and that would give me the same ratio. And then for cosecant, it would be secant of that top angle, which is pi over 2 minus theta. So this is going to wrap up the cofunction identity, that the value of any trig function at x, it's equal to the exact same thing when I use the cofunction at pi over 2 minus theta, or whatever I'm using to identify that angle that's in this spot. So I can do a ratio from down here, or I can do a ratio up here. I'm just going to use the cofunction for the other angle. That's what this identity is. So make sure you know your identities. So anytime you see a trig function that has pi over 2 and a minus and an x or a theta, can guarantee you that you're using the cofunction identities. And we're going to be looking at that in some of the problems coming up on the next page. So here's all our cofunction identities written nice and neat for you. And then from page 1, here's all our even odd identities. So again, cosine and its reciprocal are even, and these right here are odd, and the ones right over here are odd as well. So a lot of identities, maybe get some note cards. You're going to want to know these, and I know it can be overwhelming in the beginning, but with practice, they're going to get easier and easier and easier for you. So just important that you dive into the homework and you come with questions, and we're going to work all this out. No stress. You'll be really proud of yourself when you get these down. All right, so what you're going to notice in example 4 and 5 is what is inside each of those trig functions. and I see a pi over 2, I see subtraction. Instead of theta, I see x. So this is something really important for you to know, okay? Is let's just take a little side step here and talk about opposites, okay? So if I gave you 2 and I said, hey, what is its opposite? You would, of course, say negative 2. If I gave you x and I said, what's the opposite? You would say negative x. Now, this is where you want to be careful. If I gave you x minus 2 and I said, what's its opposite? Some people might be inclined to say x plus 2. Just not true. So when you find the opposite, you're taking the opposite of what you had on the other side. So because this has addition, what you're going to want to do is make sure that you distribute that negative sign. So because you have these two terms, you've got to take the opposite of each. So this ends up being, the opposite would be negative x plus 2. So we could write it this way, or we could write it as 2 minus x. So what's important to know is if you have an x minus 2, its opposite is going to be 2 minus x. So if I have pi over 2 minus x, its opposite minus pi over 2 minus x is going to give me negative pi over 2 plus x, which is the same thing as x minus pi over 2. So when I see pi over 2 minus x, I know that it has a relationship to x minus pi over 2 because they're opposites. Much like x minus 2 and 2 minus x, they are opposites. So when I look at example 4 and I look at example 5, that is the opposite of what we saw up above with the co-function identities. And so what we're going to be doing is we're going to be using those even and odd identities, because what we know is that when you put in opposites with evens, you get the same output. With odds, when you put in opposites, you get the opposite output. So let me know on Monday if you have any questions on this little precursor, but I'm going to clear this out and we're going to do example 4 and example 5 now. So I notice that I've got co-function identities in example 4. So I'm going to just write that identity. Cosine of x is going to equal sine of the other angle, which is pi over 2 minus x. Now what I'm going to do is do the substitution. So I get negative, let me write that in there, negative 0.75 is equal to sine of pi over 2 minus x. Now what you want to ask yourself is, what type of function is sine? Is it even or is it odd? And the answer to that is sine is an odd function. The only ones that are even are cosine and its reciprocal. So what do I know? That f of x is equal to the opposite when I put in the opposite. So because these right here are opposites, I know that f of x is equal to the opposite output. So if I put in opposites, I get out opposites. So I know that the opposite angle is going to have to give me the opposite output. So sine of x minus pi over 2 is going to equal the opposite, which would be positive 0.75. Now with example 5, I'm given the sine ratio, which is negative 0.37, and I notice that I'm dealing with the co-function once again. Just this time I'm starting with sine and finishing with cosine. So what you want to ask yourself is just, what is cosine? Is it even or odd? And of course, cosine is an even function. So if I'm dealing with x minus pi over 2, or I'm dealing with pi over 2 minus x, which is its opposite, I will get the exact same output. So these, I think, are easier. So I'm going to write the co-function identity. sine of x is equal to cosine of pi over 2 minus x. So I know that the sine ratio is negative 0.37, and that's equal to cosine of pi over 2 minus x. So what I know is this angle and that angle are just opposites of each other. So with cosine, if you put in opposites, because it's even, you will get the same output. So that means that if I want to know what cosine of x minus pi over 2 is, which is the opposite, I will get the same output. Because with even functions, if you put in the same value, just their opposite values, they reflect over the y-axis, and here we wouldn't have to change the sign because it's a even function. I hope that makes sense. Now we're going to go to the example 5, so I'm going to slide it up. Give me a second. All right, for our last section of the lesson, what we're going to be doing is we're going to be simplifying and rewriting trig expressions. This is going to be really important as we move forward to solving equations, solving trig equations. Okay, so what we're trying to do is build this skill in lesson 1, and then we're going to be solving equations later. So what we're going to be doing is we're going to be using a lot of good math here. We're going to be rewriting things. We like rewriting things in terms of sine and cosine. We might use some factoring skills. The thing that you're going to be asking yourselves is kind of like when you were a little kid, are we there yet? Okay, so don't fret. It's going to kind of be tough here in the beginning because you're going to be like, how do we know when we've simplified it all the way? And I'll be really honest with you, it just takes a ton of practice. So don't worry, this week's going to be a week that we're just going to be building skills. Not going to assess you on this right away, but it's really, really important that it just takes a lot of practice, and then you'll know when you've simplified it all the way. All right, so here's the deal. We've got lots of identities. We have the reciprocal identities, we have the quotient identities, we have the Pythagorean identities, and we have the cofunction identities. And what you need to know is this is just a small snip of all the trig identities that are out there. So what you want to be thinking is just identities, okay, and what those identities involve. So when I take a look at this first one right here, what I notice right here is I see something being squared. So again, I think Pythagorean theorem, a squared plus b squared is equal to c squared. So I'm going to write down the basic Pythagorean identity, cosine squared of x plus sine squared of x is equal to 1. So when I see 1 minus sine squared of theta, I know that they just manipulated this, and I know that cosine squared of x is the same thing as 1 minus sine squared of x by just subtracting this from each side. So what we're going to do is we're going to simplify this because I think that cosine squared of x is simpler than 1 minus sine squared of x. So here we go, 1 over cosine of x times cosine squared of x. And what happens here is we get a really nice multiplication problem. So this is going to be 1 over cosine of x times cosine of x times cosine of x. So this, I just wrote it twice. So when you have a fraction multiplied by that same term, these are going to make just a big fat 1, and I simply get cosine of x. And I think you'd agree that this is a way simpler form of what we started with. So that was it. Really wasn't that bad. I hope you agree. Now, looking at the second example, what I notice right here is, again, I'm looking for squares, and I notice that I've got a square right there. So what's nice is, from the past example, I see that I've got a cosine squared of x. So I'm just wondering if that's going to make things a little bit easier by using that identity. So what you need to know is you just got to try things, play around with it, and see how it works. So in tangent, right here, I know from earlier identities, I can use the quotient identity with tangent. So those are the two things that I'm going to do right there. I'm going to see how that turns out for us. So I've replaced tangent of x with sine over cosine, and the square I replaced right there using the Pythagorean identity. So this product right here is again going to make a nice 1 right there. So I get sine of x, and then I'm subtracting sine of x times what we see over there. So what I'm going to do is I'm going to be really careful, and I'm going to distribute, and I'm going to multiply the sine of x times each of those. Now what you have to be careful though is that this minus is attached to the sine of x. So minus sine of x times 1 is going to give me the minus sine of x, and then a negative sine of x times a negative sine squared of x, distributing that actually gives me a plus sine cube of x. And so because these are like terms, those are going to cancel out, and what I'm left with is just sine cube of x. So again, all I'm doing here is distributing the minus sine of x times each of those and just being really, really careful with that sign. A negative and a positive, and there's my final answer. All right, just a few more problems to get in, and we're making headway. So what I notice is I have two fractions. And so what could be better? I've got fractions, I've got subtraction, I've got trig. This problem's got it all. Now you'll remember from back in the day, to add or subtract fractions, you need a common denominator. So because their denominators are different, I know that a common denominator will be the product of the denominators. So watch what we do. I'm going to rewrite this secant of x. And I've got the 1 minus secant of x. And then I'm going to put the minus right there. And then I've got secant of x over 1 plus secant of x. So what I'm going to need to do is I'm going to need to get that common denominator. So I'm going to have to multiply the bottom and the top by the other denominator that I had to the right. So it's going to be 1 plus secant of x. And so over here, I'm going to need to multiply by 1 minus secant of x. All right, so fun times here. So I'm multiplying the bottoms. I have a difference of squares. So I'm going to get secant of x plus secant squared of x over 1 minus secant squared x minus secant of x minus secant squared x. I'm going to put that in parentheses. There's my minus. So I'm going to put that over 1 minus secant squared of x. So we're looking good. We have a common denominator, and so I did the product of this times the first and this times the second. Okay, using that good old distributive property, and I'm bringing down the minus sign. So this is something to be really careful about. So now I can combine my numerators. So I'm going to take this numerator and this numerator, and I'm going to take their difference. So here we go. I'm going to get 1 minus secant squared x, that's in the bottom, and secant of x and secant of x, their difference is 0. And I'm going to have secant squared of x minus a negative secant squared of x is going to give me 2 secant square x's. So when you subtract a negative, you're going to end up adding. So this is what we have. So again, your question is, are we there yet? So we're not there yet. So in the bottom, I notice a square and a 1. So I'm going to go back to that first identity, cosine squared theta plus sine squared of theta is equal to 1. I'm thinking of Pythagorean identity, just this one deals with secant. And I let secant has a cosine in the bottom. So what I'm going to do is I'm going to divide each side by cosine squared of theta. So I'm going to get this identity that's going to help me with that yellow one in the bottom. So I get 1 plus sine over cosine, that's tangent squared theta. And then 1 over cosine is secant squared theta. So this is really about x. So what I'm going to do is just change this to x. And this is x. And that's x. And this is x, x, x. So using this identity and subtracting secant squared of x from each side and subtracting tangent squared of x from each side, this is going to equal 2 secant squared of x over negative tangent squared of x. So let me just show that here. I've got to get this form from what I see right here. So it's just going to be a subtraction game. So 1 minus secant squared of x from each side. And then I've got to move this over to this side, which gives me the negative tangent squared of x. So this is being replaced with negative tangent squared of x. So we're almost there. Again, I know what you're asking. Are we there yet? There's been a lot of steps in this one, but you're going to get better at this. So what I'm going to be thinking is I'm going to be thinking quotient identities and reciprocal identities. So once we get to this stage right here, it's just a matter of using sine and cosine and then simplifying that. So here we go. So I know that 2 divided by a negative is going to give me a negative 2. So now I've got the secant squared of x. So I'm going to use the reciprocal identity and write that as times 1 over cosine squared of x. Now what I'm doing is I'm dividing that by tangent, so divided by tangent squared of x. So when you deal with division, I'm going to take whatever this is, and I know it's a ratio, and I'm going to change it to multiplication. I've got to flip it. So because tangent is sine squared of x over cosine squared of x, I'm going to change this to multiplication, and I'm going to take this ratio right there, and I'm going to flip it. So let's clean that up. Negative 2 times 1 over cosine squared of x times cosine squared of x over sine squared of x. So we're going to clean this up. That makes a 1. And I'm going to come over here, and I'm going to get negative 2 sine. Oh, let me fix that. So I'm going to have negative 2 over sine squared of x. So just ignore that right there. And that would be okay. But we know that 1 over sine is cosecant, so I can write this as negative 2 cosecant squared of x. So there's my final answer. If you're saying, are we there yet? We are there yet. So this problem was a monster. Just a lot of steps, a lot of identities, a lot of algebra, a lot of fraction work. So please keep calm. Know that we're gonna be just fine with this. So enough note taking. What I need you to do is really work on this day 1. and start on this day 2. Okay, we've got a little bit of catching up to do. So thank you for watching the video. I hope it's helpful. Come with questions, okay? And anything on the notes that you need me to explain again, we can do that. Start, make some headway, and get going on the homework. And good luck. See you Monday.